Electrochemistry. There are three parts in this topic, broadly speaking. One part talks about how can you make a cell. In fact, different types of cells. Second part assumes that you have got a cell and you are able to pass current because you have got a cell, and that current you pass through a solution in which ions are present, and then ions get deposited at appropriate electrodes. Part 3 talks about how the movement of ions, how does it contribute to electricity looking at the microscopic level. Just like you may look at the electron or visualize electron to understand flow of current in a metal wire, here you are visualizing ions flowing inside the solution. So three parts, broadly speaking. How do you get a cell, or how do you get different types of cells? Then if you have got a cell, or let's say if you are passing electricity through a solution of ions, how their deposition takes place, and the flow of ions contributing to current. The characteristics related to that, three parts. First, we will talk about forming different types of cells. What is the fundamental idea? Fundamental idea is the redox reaction. If you consider two species, say zinc and copper, then both are metals, so you would think that both are electropositive. But then one of them may be more eager to lose electrons than the other. That is the natural tendency. One of them may be more eager to lose electrons than the other. Say for example, you have got copper sulfate solution, and in the copper sulfate solution you place a strip of zinc metal. Copper sulfate solution, when I say, then it has got copper ion and sulfate ions. These ions are floating here and there in the solution. And now you have inserted a zinc strip. What do you find? You find that the zinc strip that you have inserted is dissolving, becoming lesser and lesser, and you find that copper is getting deposited on the zinc strip that you inserted. Copper is getting deposited, copper metal. From where did this copper come? It came from the iron, copper ion. So zinc and copper both are metals, and one would say that all metals like to lose electrons, but there is a degree of this aspect. Who wants it more desperately? Copper is getting deposited on zinc. Copper was already in ionic form, positive ion it was, and still it got deposited on zinc as metal, just copper, Cu. So copper had to gain electrons rather. Copper 2 plus to copper, it had to gain electrons. Copper is a metal, and copper 2 plus had to gain electrons, and then it could get deposited on zinc. And it did that. Zinc, on the other hand, jumped into the solution. When zinc jumps into the solution, it is going to be there as Zn2 plus. So zinc has left 2 electrons and then it has jumped. Copper 2 plus becomes copper, zinc becomes zinc 2 plus. Clearly this shows that by nature zinc is more desperate to lose electrons. Zinc is more desperate to lose electrons. That's the key idea. The redox reaction is the main thing, and who is more desperate? That makes the cell basically. That makes the cell basically. Because there are different desires to lose electrons. That natural property makes the cell. This is happening automatically. You're not really doing anything extra. Copper sulfate solution, zinc strip, it all happens automatically. It is a spontaneous situation taking place. Now, how do we get the cell? Basically what is happening is that copper 2 plus is taking 2 electrons from zinc. Copper 2 plus is taking 2 electrons from zinc. This is what is basically happening. To make a cell, don't let them come in direct contact with each other. Don't let them come in direct contact with each other. That's a smart thing to do. So copper, if you want 2 electrons, then you can't take directly from zinc because you're not in touch with zinc. So if you want to take 2 electrons, these 2 electrons will flow through some external wires. Right? And zinc, you want to give electrons, fine, but you can't touch copper and give 2 electrons. If you want to give electrons, those electrons will have to go travel via the wire and then reach the copper side. So that's what we are doing. And is it a smart thing to do? If you make two electrons travel through the external wire, two electrons for one particle, there will be several particles in the range of Avogadro number. If you make electrons travel through some wires, then you can connect whatever you want through that wire. You can connect a bulb if you want, or you can connect anything else. So the electrons have no choice but to move through that thing. Say it is a bulb, incandescent bulb. So those electrons flow through the bulb. Bulb has got a filament who has got some resistance. Current flows. I square R is the power. Heating effect takes place and light comes out. So likewise, you can think of anything else, any electrical or electronic gadget. You can connect there and electrons would flow. So isn't it a very smart thing to do? To make them not come in direct contact with each other. If copper 2 plus and zinc are in physical contact with each other, then what will happen? Two electrons from zinc will directly jump to Cu2 plus. Direct physical contact, direct jump. What do we get? Nothing, except for some heat present in the solution. Solution will get heated. What else can we get? So we are making them not come in contact. And electrons want to flow, fine. There is a wire, flow through that wire. That makes it work. The natural tendency makes it work, and the separation makes the cell work. Natural tendency, the natural redox reactions coupled with separation makes a cell work. Right? That's the basic idea. Now that you have got the idea, look at the apparatus. Instead of one compartment, you are looking at two compartments. And you can understand one is the copper side, other one is the zinc side. Now note that current is a closed loop type of situation. Closed loop type of situation. So if you just look at the outside circuit, outside wire that I was talking about, then that doesn't complete the whole circuit. What I'm talking is this. This is your external wire, and electrons would travel like this. Traveling of electrons from here to here doesn't make electric circuit. It should be a complete electric circuit here also. So maybe this I can show by dashed. That's the solution region. This is the wire region. So in wire region, the electricity is just like the electricity that you already know. It's metal, gain. But the liquid part, that would be something somewhat new to you, if not completely new. Now electrons don't flow through the liquid part. Electrons don't flow through the liquid part. Electrons flow through the metals, free electrons. Then how can we complete the electric circuit? Circuit has to be complete for current to flow. So if you are looking for connecting some bulb here, then the current should go round and round and round for maybe 1 hour or 2 hours, whatever. It should be a closed loop. It's not a transient analysis that we are doing suddenly and then gone. No. Right. So through the solution, current has to pass, and that job is not done by electrons. Electrons cannot swim. Remember that thing. Electrons cannot swim. Inside the solution, who carries electricity then? Ions carry electricity. So now look at this setup and you will understand how we are able to complete the full circuit flow of charge. So here is the setup. You got 2 electrodes, left and right. One is zinc metal, other is copper metal. Copper metal. Zinc metal is dipped in some zinc solution. Say it is zinc nitrate. So that's a zinc solution, zinc nitrate solution. And zinc nitrate solution would give ions, zinc ions and nitrate ions, Zn2 plus and NO3 minus. Then right side you have got another solution, some copper solution. Say it is copper nitrate. It's not necessary that it has to be nitrate only, some copper solution. Likewise, left side, it is not necessary that it has to be zinc nitrate. You just want Zn2 plus ions on the left solution. You just want Cu2 plus solutions on the right solution. That's why there can be so many ways to make cells. You can choose so many combinations, so many metals you can choose. Why copper, zinc? So many metals you can choose, so many solutions you can choose of those metals which are electrodes. So many cells you can make. So right side, let's say we have taken copper nitrate solution. So you have got copper 2 plus ions and NO3 minus ions. These ions are just floating around everywhere. Everywhere means copper side, these ions, and this side, these ions. But to complete the circuit, there has got to be flow of ions in this region. So I will talk about it in a moment. Now, coming to that external wire that I was talking about. External wire is the one that is going to do our job. Whatever appliance you are wanting to make work, bulb or whatever, that thing you will connect here. So wire goes from zinc, wire goes from copper, and whatever load you want, that load you can connect here. You can have a switch to control, etc. So that's about external circuit. Now, from this solution to this plate to this wire to this plate to this solution is not a complete circuit. It's not a complete circuit. Charge must flow from here to there also. So here we are. Something called salt bridge. The idea is that you don't want them to mix with each other. Right side to left side, you don't want them to really mix with each other. But you want charge to flow so that you can have a closed circuit. Now say electrons are going like this to the right side, then you want electrons to come. Electrons won't come. You want negative charge to come like that. Negative charge would come like that. Electrons going here or negative charge going here. Here, after this, it has to be ions. Negative charge should come back, right? But mixing should not take place. This solution should not mix with this solution. So you have an arrangement called salt bridge in which ions flow, but the compartments are not mixed. That's salt bridge. Now, negative should move here. But inside the solution, it is not just only the negative charge. Inside the metal, there is only one type of carrier that we talk of, that is electron, free electron. That's not so inside solutions. Inside solutions, cations also carry charge, anions also carry charge. There can be multiple cations, there can be multiple anions. So the picturization is somewhat different from electrons moving. So if we say negative charge should go to the left side, negative ion, left side fine. Positive ion going to the right is equivalent to saying negative ion going to the left. Both of them will go. Positive to the right, negative to the left. If you're wondering from where did this sodium plus come, salt bridge contains some salt. So that's how it came. So sodium is not there in any container, left or right. It's there in the salt bridge. Now let's define anode and cathode. Anode is that electrode where oxidation takes place. And we have seen that out of zinc and copper, zinc wants to become positive more desperately. So zinc electrode will be the anode. Cathode is that electrode where reduction takes place. So copper 2 plus on the right container, that will go to the electrode which is copper electrode. Copper 2 plus will go there and will catch 2 electrons. Right? It will catch 2 electrons and it will become copper. So another interesting aspect is that left side you have got zinc electrode, and zinc electrode, in zinc electrode, zinc is getting converted to Zn2 plus. Zn2 plus means inside the solution. So zinc particles from the electrode are jumping into the solution. So what will happen after sufficient time? Zinc electrode will lose its mass. It will become thinner and thinner. Especially the lower part, which is dipped, that part which is dipped. And other side, copper electrode, it will gain mass, it will become fatter and fatter and fatter, the lower side. So the masses of the electrodes would change with time. So we have defined anode, oxidation, where oxidation takes place, that electrode. Cathode, where reduction takes place. Where oxidation is taking place, zinc leaving 2 electrons right here, zinc leaving 2 electrons right here and jumping. 2 electrons are left here only, and these 2 electrons travel up. So electrons in the external circuit flow from anode to cathode. In the external circuit, they flow from anode to cathode. And strictly speaking, internal circuit doesn't really carry electrons. But if you want to visualize, saying negative charge will be more technically correct, and that will flow from this side to this side. That is cathode, right is cathode towards anode. Negative charge will flow like that, and positive charge would flow like that from anode to cathode. If you just want to visualize electrons, then it will be from here to here, though technically they are not electrons. Cathode to anode. Now, the points that I have already covered, I'm not repeating them. Focus on this point. Anode is negative and cathode is positive. Sometimes initially students have this little problem in digesting it. Anode is negative, cathode is positive. Little hard to digest for some students in the beginning. Cathode rays, negative rays. Cathode is positive, anode is negative. So how do you understand that anode is negative? It's like this. Zinc, imagine a zinc atom. Zinc atom is here in this plate. That zinc atom jumped into the solution as Zn2+. It gifted 2 electrons to the plate. Now likewise imagine other zinc atoms also. Jumping, gifting 2 electrons, jumping, gifting 2 electrons. So if this plate was electrically neutral initially, a piece of zinc was electrically neutral initially, and imagine 10 atoms of zinc jump somewhere else, 10 atoms, each atom giving 2 electrons, then how many electrons will be here in the plate? 20 electrons. If there are 10 atoms we consider, each giving 2 electrons. 20 electrons are here in that plate. They're not jumping into the solution. So shouldn't it be electrically neutral? I mean, electrically negative. So that's the reason. And likewise, you can think of cathode. Cathode was electrically neutral. I mean, this plate, let's say, is electrically neutral initially, copper plate. Now, copper 2+ comes from outside. Snatches 2 electrons from here. Snatches 2 electrons. 2 electrons gone. So shouldn't it be positive? And that is happening with so many, not just one Cu2+. Several Cu2+ are coming there and getting deposited. And each one of them is demanding 2 electrons. So cathode is positive. Right? So you will get accustomed after some time. Otherwise, cathode ray is negative, can bug you a little bit, cathode ray. But this is positive. Cathode is positive here in voltaic cell. Before I proceed, any questions? If you have, then let me know. This is a highly simplified diagram. Cathode is positive, anode is negative. Electrons flow from anode to cathode. Negative ions flow from cathode to anode, and positive ions flow from anode to cathode. We do not allow direct mixing of the two solutions, which is not going to help us really. We provide some mechanism so that the two solutions do not mix, but the closed circuit is maintained for the continuous flow of current. Porous barrier or salt bridge. So that is voltaic cell. Now, little bit of physics coming here. You know from physics that battery does work. If Q charge flows through the battery, then the work done by the battery is Q times V. Q times V. So you can also say that if work done is W, then potential difference would be work done divided by charge. That's exactly what you are seeing there. 1 joule work done divided by the charge, 1 coulomb. So that is the potential difference. You can now perhaps have a better idea about the resistance of a battery. Now imagine a battery in which ions are moving inside it. When we say resistance of a wire, electrons moving in a crystal lattice which has got ions, collisions, attractions. Electrons have a tough time when they move. So that opposition posed to them by the crystal structure, ions, etc., we have got electrical resistance due to that. And that is for something as small as electrons. Now just imagine something as big as iron. It's a bulky fellow, and it is moving right to left or left to right. It is going to collide with other ions. So now you can understand better why does a battery has got internal resistance, at least one of the reasons why battery has got internal resistance. Anyway, when we say EMF, then we say that the battery is open circuit. Then whatever is the potential difference, that is called EMF. When the battery is open circuit, meaning you are not drawing any current from the battery, then whatever is the potential difference, that is called EMF. If you are drawing current from the battery and it has got internal resistance, resistance drops potential when current flows through it, as you know from Ohm's law. So the two terminals of the battery will give you a lesser potential difference when the battery is in use because of the internal resistance coming. But when we talk about EMF, we say that it is open circuit, no current is being drawn. So even if internal resistance is there, because no current is drawn, what's the use talking about it? Any drop can only be caused if there is current flowing. Open circuit means no current flowing. So EMF word means that it is the potential difference across the two terminals or electrodes when there is no current flowing. Its full form is rather awkward. Electromotive force. It's not a force. It's not a force. But it is like potential difference type of thing. All right. Now, the solutions that we take on the two sides, left and right sides, they would be having concentration. If it is copper nitrate solution, what is the concentration of copper nitrate? Why is it important to talk about concentration? Because if there are more particles of Cu2+, then it's a common sense that there should be a lot of them going to copper and getting themselves deposited, each one demanding 2 electrons. If there are more copper 2+ ions. So if you have got higher molarity of copper nitrate solution, then that would give higher number of Cu2+ ions, and they will demand the 2 electrons. Each one of them will demand 2 electrons from the copper electrode. So it should affect the EMF. I mean, at least some common sense you can have thinking like that. Later on you will see the exact mathematics. Does it affect the EMF of the cell or not? Exact mathematics you will see. Concentration on the right side of the solution, concentration on the left side of the solution. How does each one of them affect the overall EMF? So what we do is that we make some standard conditions here also. So you have been seeing standard conditions in gases, STP or NTP, normal temperature and pressure. There it was temperature and pressure for gases. Then you saw in thermodynamics standard conditions, that bubble for H, right? And now you are seeing standard conditions in electrochemistry. 1 molar solution at 25 degrees centigrade. 1 molar solution at 25 degrees centigrade. Then the standard cell potential, for that we use a bubble, E bubble cell. So if you change the concentration from 1 molar to something else, then it could be something else. Instead of 1 molar, you can take 2 molar or 0.5 molar. So less concentration, less ions available. So how electrons will transfer, that should change by number of ions that are present in the solution. So that's how molarity should affect this. So we can talk of different E cells, the EMF of the cells under different conditions of molarity, and why not temperature? Temperature also. At least that's what you would assume. Here we are saying 25 degrees standard. Now potential difference is fine. Potential difference across 2 electrodes is fine. But we also want to talk about potential. What is the potential of right side electrode? What is the potential of the left side electrode? If I take zinc electrode having zinc nitrate 1 molar solution at 25 degrees centigrade, what is its potential? Just the zinc electrode. Likewise, just the copper electrode. What is the potential it has? You know from physics that we always talk about with respect to something. Potential with respect to what? And often we take infinity as our reference, or many times Earth as our reference. Earth zero potential we call many times, infinity zero potential we call many times. Some reference point we need always. For talking about potential difference, we don't really need any reference point. So now we want potentials of individual electrodes. So there is a half cell or an electrode which is called standard hydrogen electrode. There is an electrode called standard hydrogen electrode, and that is the referral electrode for others. So that standard hydrogen electrode has got zero potential, is assigned zero potential. It's your reference, so you assign it zero potential. In short, SHE, she. Now, if you have got that and you want the potential of zinc electrode, you can make a cell with zinc and hydrogen electrodes and measure the potential difference. Because hydrogen electrode has zero potential, whatever potential difference reading that your voltmeter is telling you, from that you can find out the potential of your zinc electrode. Hydrogen electrode is 0 volt basically. Now you may be wondering, how can you make hydrogen electrode? Hydrogen can be solid at very low temperature, which is not practical in all cases. So how can you have something like hydrogen electrode? Well, in hydrogen electrode, we don't use solid hydrogen. So we have a metal, say platinum, we have a metal, and we bubble hydrogen gas. and we immerse that electrode in an H plus present solution. So imagine some solution having H plus ions. Okay? I'm talking about hydrogen electrode. So imagine some electrode having H plus ions in its solution, and you have got platinum dipped in that, and then you have got an arrangement to pass the hydrogen gas. That is a hydrogen electrode. Now, what about standard hydrogen electrode? When we attach the word standard, then you have to take 1 molar H plus solution. You have to take 1 molar H plus solution, and the hydrogen gas that you are going to pass, that should be at 1 atm pressure. Right? So hydrogen electrode means you have got H plus and you have got hydrogen gas, but standard hydrogen electrode means 1 molar H plus and 1 atm hydrogen gas. So that's called standard hydrogen electrode, which is the referral electrode. We are still doing theory. No assignment for today. We stop now.